Hello everyone, let's analyze. So in Real Analysis 1 we talked about sequences and numbers, and today we're going to talk about sequences of functions. Of course, it's useful in understanding many elementary functions, many functions that we use in different applications and in calculus, but it's also very useful in understanding applications and analyzing different applied math problems. Let's just take a look at a simple example of why we'd want to consider sequences of functions. Suppose we have some simple differential equation that models a population. The population has a certain threshold for thriving, but there's also a capacity to the habitat. Oftentimes we use numerical methods to approximate solutions to differential equations. So we might have some endpoint approximation that defines a function which approximates my solution. And of course we'd like to know if I increase n, does my approximation converge to the actual solution? And how does it converge? And how do we describe this convergence? How do we define it? And so that's what we're going to talk about today. So suppose I have a sequence of functions that map A to R. If the sequence of numbers fn of x naught converges to a limit L, then we say the sequence of functions converges at x naught to L. So really here we're just talking about a sequence of numbers. It just so happens that the sequence of numbers is the evaluation of a sequence of functions at a particular point. Another way of expressing this idea is just to refresh our memory on what it means for a sequence of numbers to converge. For any epsilon greater than 0, there exists a natural number big N such that if n is greater than or equal to big N, then fn of x naught minus L is less than epsilon. Right? So that's putting the definition back into the language of sequence convergence. So let's take a look at an example. Suppose fn maps the closed interval 0 to 1 to R, and we define it as fn of x equals -1 to the n times x minus 1/2. We'll draw a picture. Suppose this is 1, this is 1/2. Well, if n is even, then -1 to the n is +1, and I just have x minus 1/2. So this is f even. And if n is odd, I have negative x minus 1/2. I get exactly that. F odd. So when n is 1, I get this function. When n is 2, this one, 3, 4, 5, 6. We see the function just flips flops. However, at 1/2, it stays the same. Since fn of 1/2 equals 0 for every natural number n, we could say that the sequence of functions converges at x naught equals 1/2 to 0, because that would generate the sequence 0, 0, 0, 0 repeated infinitely. However, Fn does not converge anywhere else. So we just saw a sequence of functions that converges at a single point to a number, but nowhere else. So we can't say that that function converges in any way to another function. So what does it mean for a sequence of functions to converge to a function? Well, if the sequence of functions converges at all x in the domain to f of x, then we say the sequence of functions converges piecewise to f of x. Another way of describing this for all x in A, and for all positive epsilon, there exists a natural number n. Now let's just pause here and notice that this natural number n is going to depend on epsilon, but it also depends on x. For all x in A and for all epsilon, there is a n. As epsilon changes, the n that exists may change. As x changes, the n may change. Such that little n greater than or equal to big N implies fn of x minus f of x is less than epsilon. And let's record our observation. The choice of n that guarantees this result depends on epsilon and x. So let's consider an example. Let's consider the sequence of functions defined on the closed interval 0 to 1, defined by fn of x equals x to the n. So this sequence converges pointwise to f of x is equal to 0 if x is greater than or equal to 0 and strictly less than 1, and 1 if x equals 1. So let's take a look at what these functions look like. So let's take a look at those sequence of functions. I claim that x to the n, and we see illustrated x to the 1, the first function in the sequence, converges piecewise to the function that is 0 from 0 to every number strictly less than 1 and 1 at 1. So we can see that as n increases, the function does grow increasingly close to the blue function. Every number strictly less than 1 is eventually going to converge to 0, And fn of 1, of course, is 1 for every n. So it just stays right there at f of 1, which is 1. If this went on forever, this would be a very long video. But also, the red function would match exactly the blue function. So we just saw an illustration of the fact that x to the n does appear to converge to f of x pointwise. But let's prove it rigorously using the definition. At x equals 0, fn of 0 equals f of 0, which specifically equals 0 for every n. Similarly, at x equals 1, fn of 1 equals f of 1, which equals 1. For x strictly between 0 and 1, let epsilon be positive. So our goal is find a natural number n that guarantees when little n is bigger than big N, then x to the n minus f of x, which equals x to the n minus 0, because f of x for these particular x is 0, right, is less than epsilon. So my goal is to find a n that guarantees this result. Whenever this is true, this is true. So suppose I took the log base x of both sides. Now you may notice when I took the log base x of both sides that this flipped. That's because for x strictly between 0 and 1, log base x is a decreasing function. By the way, let's remind ourselves, what is the log base x? Well, the log base x well, the log base x asks a question. X raised to what power equals the argument? So this question says x raised to what power equals x to the n? Well, of course, x to the n equals x to the n. So I just need to make sure that n is larger than the log base x of epsilon. Therefore, let big N be greater than the log base x of epsilon. And notice that big N depends on both x and epsilon. If n is greater than or equal to big N, then x to the n is less than epsilon. Now at this point we should make an observation. If a sequence of functions converges to f pointwise, then for every x in the domain, the sequence fn of x, which by the way is a sequence of numbers that converges to f of x. And if a sequence converges, the sequence is Cauchy. So there's a stronger notion of convergence called uniform convergence. Suppose A is a subset of the real line, and Fn maps A to R. The sequence of functions is said to converge uniformly to F if, for any epsilon, there is a natural number n for which n greater than or equal to big N implies that Fn of x minus f of x in absolute value is less than epsilon for every x in the domain. And the key notion here is for every. The same capital N works for every x. Before, for point one convergence, for every x, there was a capital N that works. But here, there is a capital N that guarantees my less than epsilon condition for every single x. And that's the key difference. So let's consider the same function we just looked at. Fn equals x to the n for x in the closed interval 0 to 1. We know already that this function converges pointwise and by the way, a bit of notational shorthand, Fn to f pointwise means the sequence of functions Fn converges to f pointwise. Right, we know converges to f of x defined by the piecewise function 0 if x is strictly less than 1 and 1 if x equals 1. But does it converge uniformly? Let's take a look. We know that the function fn of x equals x to the n converges pointwise to f of x marked there in blue, 0 if x is strictly less than 1 and 1 otherwise. In other words, if I were to mark out any point, and in fact I did mark out 10 points, each of those points would converge to f of x. So we see all of those red dots, which are for x strictly less than 1, they converge to 0. And of course, the blue dot is 1 for all n. Fn of 1 is 1, and so is f of 1. So we see an illustration of pointwise illustration. But Fn of x does not converge uniformly to f of x. Let's see and understand why. If I wanted to show that Fn of x equals x to the n converges uniformly to f of x, illustrated in blue, I would have to show that there is some value n for which Fn of x is completely within the dashed lines for all x less than 1 and between the black dots for x equals to 1. But as we're going to see illustrated, I can find a value of x that's always outside of the epsilon bound. In other words, for every n, there is some x for which Fn of x minus f of x is strictly greater than this particular epsilon. And of course, all I have to show is that this is true for a particular epsilon to show that Fn of x does not converge uniformly to f of x. In fact, imagine that Fn of x did converge uniformly. As I said, my red function would have to be completely between the dashed lines for x less than 1, but still be between the black dots for f of 1. Well, that would necessarily require a jump discontinuity at 1. But x to the n is continuous for every n. However, f of x is discontinuous. So there's no way that x to the n can converge to something discontinuous uniformly. In fact, we'll prove that result shortly. So let's prove that Fn of x does not converge to f of x uniformly. In other words, let's prove that this definition is not true. So to negate the definition, we would have to show there exists an epsilon greater than 0 so that for every n, there is an x for which x to the n minus f of x is greater than or equal to epsilon. Now, this equals x to the n if we choose x to be less than 1. And we will. I can find an x less than 1 for which this is true for every single n. Well, x to the n is greater than or equal to epsilon if x is greater than or equal to the nth root of epsilon. Suppose that epsilon were to equal 1/5. If x is in the nth root of 1/5, but strictly less than 1, then x to the n minus f of x, by the way, f of x here is 0, equals 1/5. Reason it equals 1/5 is because the nth root of 1/5 raised to the nth power is just 1/5. Well, actually it's greater than or equal to 1/5 if I choose any x here. Which is my epsilon. And so because for every n I can always find an x to break my less than epsilon condition, fn of x is not uniformly convergent. So we just saw an example of a function that was pointwise convergent but not uniformly convergent. So let's take a look at another example. I claim that this function is indeed uniformly convergent. That fn of x is equal to n sine of x plus sine n times x divided by n converges uniformly to sine of x on the domain 0 to 2 pi. So let's take a look at this function and see if we can visually understand why it's uniformly convergent before we prove that it satisfies the definition. So here we see an illustration of our function f of x in blue and f1 of x in red. As n increases, we can see that fn of x grows closer and closer to f of x. And hopefully we notice that it does so uniformly in the sense that there's no one point that lags behind the rest. So let's take another look at our sequence of functions. Here we see in blue again f of x, and we see in red f1 of x. Now let me choose a particular positive epsilon, and I'm going to show that, at least for this epsilon, fn of x is going to be completely within my f plus epsilon and f minus epsilon bound. Not yet, not yet, not now. We see that the red function fn of x is completely within an epsilon range of f of x. Now, of course, I only showed that that's true for a particular epsilon, but I claim I can actually do it for any epsilon. Let's show that. So let epsilon be positive. Of course, it's arbitrary. Our goal is to find a natural number n to guarantee that when little n is bigger than big N, then fn of x minus f of x is less than epsilon. Right, so my goal is to find this n for which this is true. Right, that's my singular goal right now. Well, fn of x minus f of x is n sine of x plus sine n times x minus sine of x. Well, this is over n. To have a common denominator, let's multiply this by n. N sine minus n sine, they cancel. And I get sine of n times x over n, which, by the way, is less than or equal to 1 over n, because sine is bounded by 1 above and negative 1 below, so the absolute value is bounded above by 1. Now, I want 1 over n to be less than epsilon. Well, then let me just choose n to be greater than 1 over epsilon. Right? Of course, every number, right, has a natural number above it. Then if n is greater than or equal to n, fn of x minus f of x, as we just pointed out, is less than or equal to 1 over n. And if n is greater than or equal to big N, 1 over n is less than or equal to 1 over big N, which is less than or equal to epsilon, and we've proven our result. Now we should point out here, we'll make a note, if fn converges to f uniformly, that implies that fn converges to f pointwise. Uniform convergence is a stronger type of convergence. However, as we have already seen, if fn of x converges to f of x pointwise, that does not imply that fn converges to f uniformly. Okay, and today's main theoretical result is that if a sequence of continuous functions converge uniformly to a function f, then that function f must be continuous. So let's prove this. By the way, this gives us an alternate way of showing that x to the k on the interval 0 to 1 cannot converge uniformly to f that is 0 for x less than 1 and 1 at 1. It would violate this theorem. So my goal is to show that for any epsilon greater than 0, there exists a delta for which x minus x naught is less than delta, implies f of x minus f of x naught is less than epsilon. Here x naught is an arbitrary element of the domain A. All right, so that's our goal, right? When we've shown this is true, we can stop. Now, what do we know? We know that Fn is continuous, and we know that Fn converges to F uniformly. Well, let's take a look at this result. Let epsilon be positive and of course arbitrary. This fact implies that there exists a natural number n for which fn of x minus f of x is less than epsilon over 3 for all x in the domain A. Right? This comes from the uniform convergence of the function result. Now, the fact that fn is continuous for every n means there exists a delta, and this delta is going to be the delta in our goal. It's going to be the delta that ultimately brings us to the glory of continuity of f. Such that if x minus x naught is less than delta, then fn of x minus fn of x naught is less than epsilon over 3. So again, this result came from the uniform convergence. This result came from the continuity condition of fn. Now, let's start working towards our goal. F of x minus f of x naught equals, and here's where we start adding all of our cast of characters. F of x minus fn of x plus fn of x, and by the way, all I've done is add 0 here, minus fn of x naught plus fn of x naught minus f of x naught. Now, by the power invested in me, by the triangle inequality, this is less than or equal to f of x minus fn of x, absolute value, plus the absolute value of fn of x minus fn of x naught, plus fn of x naught minus f of x naught. Now this term here, we know, is less than epsilon over 3 for this n that's guaranteed to exist. Right, so that is less than epsilon over 3. This term here, by the continuity of fn of x, we've also guaranteed is less than epsilon over 3, so long as this condition is true. And this term is less than epsilon over 3, also by the uniform convergence. Now this says x naught and this says x, but this is true for all x in A, and x naught is an element of A. So it's true here. Therefore, there exists a delta, and if x minus x naught is less than delta, then f of x minus f of x naught is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is equal to epsilon. We now have all the elements of our goal for any epsilon, and here epsilon is arbitrary. There exists a delta, here it is, and whenever this is true, this is less than epsilon. We have our goal. We can also use the idea of pointwise and uniform convergence of sequences of functions to talk about series of functions. Just so that we're on the same page, When I say a series of functions, I mean an infinite sum of functions. Of course, an infinite sum of functions is really the limit of a sequence of functions where the sequence of functions are partial sums. We say a series converges pointwise to f if the partial sum converges pointwise. And we say a series converges uniformly to f if the partial sum converges uniformly. So let's take a look at an example. Let's consider a sequence of functions defined on the open interval -1 to 1, where fn of x is equal to x to the n. Let's show that the series converges to 1 over 1 minus x pointwise. Well, the partial sum Sn of x is defined by the sum from j equals 0 to n of x to the j. And we actually have a formula for that. It's equal to 1 minus x to the n plus 1 divided by 1 minus x. Now, you've probably seen this before. You've probably seen this equality before, perhaps in a calculus class, perhaps in a different class. But just as a quick reminder, we'll put this in a parenthetical. We can see this equality by taking this partial sum and multiplying times 1, specifically in the form of 1 minus x times 1 minus x. And we'll see that we get the identity we just have. Once we take the summation and multiply by 1, we have this summation. If we take the summation and subtract by negative x, well then we get what's essentially a telescoping sum, and only the first and last points remain, and the denominator remains. Now my goal for positive epsilon, find n such that if n is greater than or equal to big N, I get that Sn of x minus f of x is less than epsilon, right? So my goal is to find this n that guarantees this result, right? So I have to be on the hunt for this n. That's my goal. Because I'm going to prove that my convergence is pointwise, it's likely that my n is going to depend both on epsilon and on x. Well, what is this equal to? Sn of x minus f of x equals 1 minus x to the n plus 1 minus 1 minus minus, that's a plus, x to the n plus 1 I'm sorry, just minus 1 divided by 1 minus x, because f of x and Sn of x have a common denominator. 1 minus 1, of course, is 0. I get x to the n plus 1 divided by 1 minus x, which is less than or equal to the absolute value of x to the n divided by 1 minus x. Now, why was I able to take this absolute value and put it here just around x? Well, because the absolute value of this quotient is the absolute value of the numerator divided by the absolute value of the denominator. And because x is strictly between -1 and 1, the denominator is positive. And the absolute value of x to the n plus 1 is the absolute value of x to the n plus 1. The absolute value of x to the n plus 1 is the absolute value of x to the n times the absolute value of x. And the absolute value of x is strictly less than 1, which is why I get this. And of course, x to the n divided by 1 minus x is less than epsilon if and only if x to the n is less than epsilon times 1 minus x. Well, that's true if I take the log-based absolute value of x of both sides By the way, the absolute value of x is between 0 and 1. Strictly between 0 and 1. So it's a decreasing function, which means this sign flips. Log base x, epsilon times 1 minus x. Now you might be wondering, wait a second, why can I say x is strictly between 0 and 1? We understand why the absolute value of x is strictly less than 1, but can't the absolute value of x be 0? Well, of course it could, but for x equals 0, we essentially have the sum of 0 to the n from 0 to infinity. And we're defining 0 to the 0 to be 1. So of course we get that is equal to 1 divided by 1 minus 0. Now remember, log base absolute value of x as, that parentheses needs to be here, the absolute value of x to what power equals the absolute value of x to the n? Well, the absolute value of x to the n equals the absolute value of x to the n. So I need n to be greater than this number. Well then, if I choose n to be an integer strictly greater than the log base absolute value of x of epsilon times 1 minus x, then if n is greater than or equal to n, which is strictly greater than that, we get that Sn of x minus f of x, we already know that that's less than the absolute value of x to the n divided by 1 minus x, which is less than or equal to the absolute value of x to the capital N divided by 1 minus x. And capital N is strictly bigger than this number, so you get this is strictly, that this is strictly less than, if I replace n with something smaller, divided by 1 over x, and this equals epsilon times 1 minus x divided by 1 minus x, which equals epsilon. So if n is greater than or equal to big N, and n is greater than or equal to this number, then my partial sum minus my limit function is strictly less than epsilon. And we've proven our result. Now I claim that my series does not converge uniformly. However, if for a strictly less than 1, we restrict the domain to negative a to a, then on this domain, my series does in fact converge to 1 over 1 minus x uniformly. Now, I would challenge you to try and show these two results over the weekend after you watch the lecture. And perhaps we'll discuss it Tuesday in class. That's it for now.